So I guess I better start off by introducing myself and how I got to where I am. So I built and run a SaaS platform called Tutor Cruncher, which is a monolithic Django app running on Heroku, using RQ for doing worker tasks. We've now, as we've grown, built a bunch of microservices outside that using AIOHTTP and a bunch of other libraries. As part of that, in that process, over the last 3 or 4 years, I've become a contributor to AIOHTTP and to RQ and built a bunch of libraries of my own, in particular ARQ, which is an async IO successor to RQ, or I would say successor, and Pydantic, which isn't really relevant but is quite popular. So I wanted to give this talk because I got a long way as a developer without really understanding the landscape of how parallel programming works within Python and also in general. And so I wanted to kind of give a high-level introduction. So I'm going to talk about the 4 levels of concurrency, or the main 4 levels of concurrency that I see. I'm going to demonstrate each of them with Python, and I'm going to try and explain why you might use them and why you might not use them, and I'm going to try and keep it mildly entertaining. What I'm not going to do is try and prepare you for a computer science exam on distributed computing, or read the spec to you, or talk about the protocols. This is going to be quite high level. You're going to have to bear with me on that. So why is parallel processing important? I think this graph kind of demonstrates it. This is the spread and average speed of CPUs over the last 25, 30 years. What's interesting is that Python was conceived pretty much on the left-hand axis of this in about 1990, when most computers had 1 CPU and when CPU speeds were increasing really quickly. In around 2005, that effect plateaued, and suddenly we started getting multiple CPUs in computers, both in servers and in desktops. I guess that was partly because people wanted it, and it was really because the CPU manufacturers needed something new to sell. And so at that point, Python had to adapt and had to implement multiple processing, parallel processing. But the kind of interesting thing is that it didn't start off with that. It had to retrofit it later, and you can still see a few of those bugbears now in the GIL and stuff, as I'll speak about later. Only other thing to mention is that the right-hand side of this graph, the kind of pickup recently, may or may not be right. I think this data they might have done benchmarks on high-end processors more recently than on other ones. So that might be why there's that uptick at the end, but I'm not sure. So no talk could be complete without a NAF metaphor. And so Kind Tom, who works for me, has built this metaphor in Minecraft. So the principle here is that we're thinking of a factory like a computer. We're thinking of a process like a conveyor belt within a factory. We're thinking of CPUs as a bit like individual people working on those production lines. And then we're thinking of networking as the trucks coming to and leaving the factory. So the highest level of parallel programming is multiple machines, or computers, or virtual machines, or containers. Anything where the code sees itself as running on a specific computer. And this is demonstrated here with factories as multiple different factories. So instead of building one factory bigger, you have multiple factories all running independently, but perhaps networking between each other. So in this case, they're not networking between each other, they're just doing their own thing. You can imagine scenarios where we do that quite a lot. So for example, front-end servers on a web platform would generally talk to the database and talk to the client and use things like cookies for state, but they wouldn't actually talk to each other. They wouldn't know how many other machines were running around them. But quite often they do have to communicate, and that is where the communication comes in. So to get to an example, we're using RQ here. I promise you this is the smallest text we'll go at any point in this presentation. I hope you can all read it. So RQ is a queuing library built with Redis, as the name indicates. In particular, it uses Redis's lists to do the enqueuing. So to enqueue a job, you push it into one end of the list, and to execute a job, you pop it out the other end of the list and then execute it. So the code we're going to use for most of our worker examples here is in the top file here, worker.py. It's very simple. It just downloads a web page, in this case from Python Europe, for one of the last few years, takes the text, and counts the number of words. So splits it and then counts the number of elements in the resulting list. Very simple. In reality, you wouldn't need multiple machines or even multiple anything to do this, but that's our example. Below you see the code we would use to enqueue those jobs using RQ. So we take a completely vanilla Redis connection in this case. I'm demonstrating it here on my laptop, so I'm not actually running it on multiple machines. I'm running it on multiple processes to demonstrate the principle, but bear with me. And then we're, for each of the last 4 years, enqueuing a job where we run count words. Now, one of the interesting things to see here is that even in our RQ example, which is running on the main machine, not the worker, we have to have access to the count words function so we can import it, so we can enqueue the job. So if we look at running that below, first thing we do on the right here in our two workers is we call RQ worker, and that starts the worker, which is doing a blocking pop from Redis, waiting to execute the jobs. To enqueue those jobs, we simply call our example here, RQ worker, that bangs those 4 jobs into the queue and prints out the result, which is what RQ gives us that we could use to get the actual result later. And then you see those jobs being executed in our queue here, and if you can see closely enough, you can see the years and how many words. It's not very interesting, but there we are. So the advantages of multiple machines, scalability is the big thing. You can add machines very easily. Also, adding machines has a linear cost. If you have 10 machines and you want an 11th, it gets 10% more expensive. And lastly, isolation, which is demonstrated here with our factories. If one of your factories were to blow up, you can simply add another factory on the side, or in the case of Minecraft, pan to the left, because adding a new factory in real time is too hard. Disadvantages of multiple machines, well, mainly complexity. You have to set up all your networking between your machines. That's made very easy by platforms like Heroku and others, but it still can be a problem, particularly during development. And so, as you saw earlier, quite often we use multiple processes to simulate multiple machines. So to go on to multiple processes. This is within a single factory running multiple production lines. In our analogy, processes are an operating system concept, and they're designed to keep different programs isolated from each other whilst running at the same time. So they were developed for, I guess, originally for desktop applications where you were running 2 completely separate things, but you can use them to run the same code in parallel. So here's our example. You see immediately it's quite a lot longer. And the other main difference here is we're not using an external library for the queuing. We're using Python's standard multiprocessing library, Python's standard process, and joinable queue. So we have exactly the same code here for adding up stuff, for counting the words. Then we have our very rudimentary worker, which is just a loop that runs taking jobs out of a queue and either executing them, or if the job is none, that's our queue to quit. And so to enqueue those, we have to create our processes. The really interesting bit here is happening on line 20. What Python's doing in the background there is forking the main Python process to form multiple sub-processes which at that point share memory, but any further changes of memory would be copy on write, so they would be changed. So we now have completely separate processes, and that new process is set off to run our worker function we just saw. With the argument in this case is just an ID to tell us what worker we're running. Enqueuing our jobs is simply as simple as doing put on our queue object that Python has helpfully given us. We can then wait for that queue to be empty, for all of the jobs to be finished. Then we have to go about putting the none job into each of those queues to stop them, and then we wait for our processes to finish. And you see there it printing out our words as it did before. Again, not very interesting. So the advantages of processes, they're really easy to run. No networking required. You get this OS level guarantee that your multiple different processes are isolated. They can't share memory after they've been forked. And they're pretty fast to communicate, either by doing networking on a machine or multi-process, inter-process communication, all very quick, compared to multiple machines, I should say. But the disadvantages of processes are quite significant. You have very fixed limits to scaling. If we go back to our factory analogy and we want to add another production line into our factory, there's nowhere to put it. If we want to have 4 production lines, we need to build a whole new factory, I guess, decommission our old factory, and start running our new factory. If we want to go back to having 3, then I guess we have to ignore our new 4 production line factory and go back to the 3. And secondly, it gets really, really hard to build a really, really big factory. So we can make it 5 times bigger or 10 times bigger, but it gets prohibitively expensive to have a 1,000-core machine. So it's not linear to scale. Whereas you saw with multiple machines, it was linear. And again, we don't have isolation. If our machine breaks, the whole thing's broken. So next we go down to multiple threads. So threads are a way of achieving concurrency from within one process. They come in kind of 2 variants, kernel threads and user threads or green threads. When we talk about threading in Python, we're talking about kernel threads. So it's important to remember that kernel threads are the only way from within a process to run a task on 2 different CPUs at the same time. So we can do lots of things that look like parallel, but unless we have kernel threads, we can't be running things on 2 different CPUs at the same time. And in our analogy here, our production line has changed shape, and you see we have 3 of these boxes that technically have faces, and they're supposed to represent the workers. So we're running multiple things on the same process. So our threading example looks suspiciously like our multiprocessing one. That's not a coincidence. Python's tried quite hard to keep the interfaces the same between processing and threading. So we have the same function as before. We have exactly the same worker, except we say quitting thread instead of quitting worker. The difference is our imports. So we're importing here from queue and from threading to use those versions rather than the multiprocessing variants. This is all basically the same, except obviously line 21, where we create the thread, we're creating a secondary subthread within the same Python process instead of creating multiple processes. Again, we bang the years into the queue to run the workers, wait for them to finish, kill the threads, and wait for them to have been killed. And we get the result again. So the advantages of threads, they're lighter, even lighter than processes. They're faster to create and faster to switch between, and they share memory, which can be an advantage, but can also be a big disadvantage. And so disadvantages is kind of exactly the same thing. They share memory. So memory locking is horrid. To use a Go proverb, communicate by sharing memory. And so, do not communicate by sharing memory, share memory by communicating. So we can do that with Python threading. Python provides some primitives for doing communication between threads that is secure. But if you're not careful, it can all go wrong, and you won't get a nice warning. It'll just burst into flames. The second and bigger problem that is specific to Python is the global interpreter lock. So from the Python wiki, the GIL protects Python objects, preventing multiple threads from executing Python code, more than one thread from executing code at once. What? So the whole idea here was we would run stuff in parallel, and now we've heard about this lock thing that prevents us from doing that at all. Let me try and demonstrate that with another example. We've taken pretty much the same code, but instead of doing a network request, now we're doing something CPU bound. So in this case, counting a bunch of numbers, and we're using standard Python sum for doing that. And we're going to do that in 2 ways. One, we're going to do that in a normal for loop, just doing that task 4 times, and in the other case, we're going to go through all the palaver of creating our threads and running them in parallel. What happens? Well, it's not very exciting. We actually get exactly the same time. In fact, it's even slightly quicker to do it without multiprocessing, without multithreading, because we don't have to have the overhead of creating the threads. All is not lost. You can do this same task with multiple threads and make it quicker. Here we're using NumPy. So NumPy's sum function is going to do the summation in C. C in turn can release the global interpreter lock, and so here we can get the advantage of multiple threads. So it's going to be quicker because it's done in C, but also we see here that we nearly halve the time by doing it in multiple threads. So I guess the not quite half is that the overhead of creating those different threads. And so anything where we can release the global interpreter lock because we're executing in C, or where we're doing file I/O tasks, or we're doing networking, threading can help. But in pure Python CPU-bound tasks, doesn't really help. So lastly, we come to the 4th level of parallelism within Python, but also not necessarily unique to Python, which is async I/O. I think this is really cool. I am obsessed by async I/O. I think it's wonderful. And I will try and persuade you that it's the way to go for lots and lots of things. The idea here is we're doing cooperative scheduling. So we have one kernel thread, but within that, we have some wonderful tools that allow us to seem like we're doing things at the same time, when in the background, we're actually only executing one bit of code at a time. To do this, we have an event loop that's effectively scheduling tasks in a way to keep something happening all the time. So I promise you I won't carry on pushing the metaphor any longer after this. But without async IO, you see here in our top example, when we're doing networking, our thread has to stop. Because it is waiting for the networking to come back and give us our response, that thread and perhaps that whole process has to stop and wait for the networking to have finished before it can go on and do something else. With async IO, on the other hand, our thread can carry on processing as networking tasks are going on, because our event loop is doing a clever job of scheduling tasks to fill in the gaps. So an example, first of all, you immediately see it's already shorter than our examples before. We don't have to do half as much faff and setup. We do, however, have to call our coroutine using, in this case, asyncio.run. If this was JavaScript, you could just set off your coroutine and hope for the best, and it'll finish in the end and no one seems to mind. In Python, you have to either await a coroutine or set it off like this if you haven't got an event loop running. So our main coroutine is simply calling our count words coroutine, which I'll get to in a moment, and putting the result of that, which is a future, into a list. And then lastly, we use the special coroutine asyncio.gather to wait for the results of those 4 coroutines, and once they've finished, proceed. So how does count words work? And here we get to the big problem with async IO. We can no longer use requests. We've had to rewrite this function entirely. In this case, we're using AIOHTTP. We have to create our session explicitly. In this case, request did it implicitly. Then we do our get request. We get back, this is a context manager or an asynchronous context manager. We get our response. We can then await reading the text off the network for the response to that. And finally, we can do the same thing as before and count the number of words on our page. And you see the result again. So advantages of async IO, even lighter than processes and threads. We can quite happily have, say, thousands of WebSockets connected to a single host, processing all of them without enormous amounts of CPU or memory usage. They're a lot easier to reason with because you are explicit about where you're going to go and do some networking, where your current piece of code is going to release and do an await, and so other code might get executed when you're doing networking and when you're not doing networking. And there's technically less risk of memory corruption because we're only ever running one bit of Python at a time. Disadvantages, well, we don't get any speed up of CPU at all by using vanilla async IO, but the real problem is a whole new way of thinking, and in general you have to kind of rewrite applications. It's possible in theory to adapt them, but in general I think you basically have to abandon an existing project and start again if you're going to start using async IO all over the place. You might be able to get away with using it in a few places, but in general it's a whole new rewrite. The point here is the whole brilliant thing about async IO is that it's explicit, but that means it can't be implicit. You can't have some library that wraps around async IO. There was someone asking it on Python ideas recently, can't we make it implicit? The whole point is it's not. The point where it gets really tricky is where all of these 4 levels of parallelism interlink with each other. So machines, the RQ example I showed you, RQ actually does forking in the background to run its worker. The multiprocessing joinable queue that I showed you is in fact using a thread in the background to do to put things into the queue. Async IO has ThreadPoolExecutor and ProcessPoolExecutor that I'll show you in a minute. Machines, when they're communicating with each other because it's networking, you then want to go into the async IO world, and there's ARQ and AIOHTTP that do that. But all of these things interact, and so it can get a bit confusing kind of where we are. I want to talk about one of the uses of async IO that I don't think enough people are talking about, which is in being a sane way of doing multiprocessing and multi-threading, particularly multi-threading for file operations and multiprocessing for CPU-bound tasks. You get all of the performance improvements from threading or processes, but from the comfort of async IO, and it's much easier to reason with. So we have an example here. We're using our same do calcs as we had just now in NumPy, so we know that that is suitable, that's a candidate for multi-threading because it releases the GIL. But instead of just calling our coroutine, we now have to create this ThreadPoolExecutor. That's creating a pool of threads in which to run our tasks. And the clever bit is run an executor, which returns a coroutine that waits for the task to be completed within the thread. And there's a process pool executor, which has exactly the same uses, just a different name, and is obviously creating multiple processes and doing it that way. And so we create this list of coroutines, and again, gather them, wait for them all to be completed, and hey presto, we get a time. Again, we get the speed up of multi-threading, but from the comfort of async I/O. So in summary, I think I've probably not taken up half enough time, have I? I don't have a clue. We've talked about the 4 levels of concurrency. We've said that they're all possible with Python. None of them are unique to Python, but they're all possible. Async I/O, I think today Python is probably leading the way in its ease, at least, even though it came to the party late. I think it's kind of accepted as one of the best implementations of that. I definitely think it's cleaner than what's going on in other languages, except for arguably JavaScript, but that has its own problems. They all have their strengths and weaknesses, and the key thing is to work out which one you want to use for a particular application, and that they often interact with each other. So they're not unique. They don't get to stand in their high castle and be on their own. They're all interlinked with each other. But the real point I was trying to get across today is that there's this landscape of different processes, and process is a bad word to use, of different tools out there, and you need to have a bit of an understanding about what they're doing. Just taking the first working example off the top of the page, putting it into an editor, pressing run and seeing what happens, gets you a long way. It got me to a company that pays my salary, but it's not always the best way, and it becomes a problem when everything goes wrong, and you're trying to understand what's happening, and you have no grounding because you've just taken the example and got it to work, which is definitely what I did the first time round. So thank you very much, and I guess we've got lots of time for questions. If we've got, having said questions, if we've got a couple of minutes, I'll do a little tiny bit of advertising some packages I've built since we got a second. So ARQ is a successor to RQ, but it uses async I/O, so it uses the async bindings for Redis, and it allows you to enqueue tasks from AIOHTTP application or similar. It also has some other useful features, so it has this principle of every job has to be finished, so it might be run multiple times, but it has to be executed. It doesn't actually use a list, it uses a sorted set, which means you can enqueue tasks to be run at some point in the future, and if they get stopped, it automatically reruns them again when it comes back up. DevTools, I think, is the most interesting thing I've ever written, and no one seems to care at all, so I'd love your feedback on it. It's basically a better print command that tells you the line where it happened and what you printed, and prints it in a pretty way. I use it all the time, but I failed so far to persuade anyone else it's interesting, and Pydantic is quite widely used as a type hinting using Python, data parsing using Python type hints. Thank you. Now questions.
We have lots of time for questions, so we also have 2 microphones over there. You can probably see them. But, so please line up. If you have questions, line up behind the microphones, and we'll be able to take a number of questions. Quite a number of questions. I see we have 1 question, so go for it.
Maybe I didn't understand you well, but you said there is no good tooling to do machine level parallelism.
Say again?
But as I understand, Celery is exactly the tool you can use to do your to run your parallel workers either on a single machine or on a lot of machines.
So what I was saying is that there's no, built into the standard library, there's no way of doing the cross-machine communication over HTTP or some other protocol. There are some great libraries, but they're not built into the standard library. I think that's actually one of the reasons it's been so successful is that external libraries have to compete on being really easy to use and on iterating quickly and taking advice, whereas the standard library has to be slow-moving and has to be short and has to not respond to advice half as quickly. So actually, I think it's in some ways a good thing. Maybe multiprocessing would be way easier if there was the equivalent of requests, one library everyone used that was designed to be super easy.
Okay, thanks.
Hi. So I have two questions regarding RQ. I'm already using RQ, and I was going to ask first, does it make sense for me to switch to RQ as a drop-in replacement if I don't use any async IO? That's first question.
Using RQ?
I'm using RQ now. Can I just switch to ARQ for my completely synchronous code? Does it make any sense to switch to ARQ for this?
I mean, you could do. If you want its more advanced features like running tasks sometime in the future and re-enqueuing the job if the worker shuts down, you can do. You might want to go and use ThreadPoolExecutor or ProcessPoolExecutor from within a particular job to do that job in parallel. But in general, ARQ, actually same as RQ, is only running, per process, it's only running one job. Well, RQ is running one job at a time per process, and it thinks you run another Heroku worker or whatever it might be, or another job in another terminal to run multiple workers in parallel. ARQ will run up to 60 jobs at the same time using async IO, but obviously if your task is not networking or suitable for async IO, then only one is actually going to be running at any one time.
So actually that was my second question. So if I still have just synchronous code, it will still be run one at a time, unless I fork multiple workers anyway, right?
Yeah,
okay.
Exactly. Either you run multiple workers or from within a job, you call ProcessPoolExecutor or ThreadPoolExecutor.
Okay, thank you very much.
Maybe we're finishing early.
Never. No. Any further question, folks?
Yeah.
Oh, yeah, go for it. I can give you the microphone.
Is there any advantage to having a flattened list of coroutines that you want to run as opposed to calling a couple of different coroutines which themselves gather a list of coroutines, or does it not matter as long as it's running on the same event loop?
It basically doesn't matter. I guess there is some overhead to running a coroutine, but it's so small that if you're worrying about those kind of steps, you need to go write it in C or Rust or something. In general, don't worry about it. That's not going to be your problem. I mean, at some limit of, as I say, at some limit it will become, but at that point you're going to do it another way probably.
Any further question? Otherwise, I have questions.
Okay.
I can ask you, can you tell us a little bit about some sample use case, real-world use case for, say, ARQ, like you use it in your job, if you can talk about that, or how you have seen people use it?
So we use it for sending emails. So TutorCruncher, the company I run, we send, I guess, about 1 million emails a month. Not a great deal, but at points it gets to quite high load. We are currently tethered to Mandrill, although they are awful and I hate them because our 300 customers have all set up their DNS records to send emails from Mandrill, so moving over is going to be hell. About 5% of emails you try and send through Mandrill, you get back 502 or 503, or just a broken HTTP request. And so we're using ARQ both to go and send lots of emails quite fast, but also to back off and retry those jobs when they inevitably fail quite a lot.
And so does ARQ, for instance, have the facility to requeue the failed jobs for you and
let me try,
that kind of stuff?
Since we've got time, let me try and get up. That's working, isn't it? We're going to get in the internet? Yeah, we are. Oh, no, I did not want to do that. So here's an example of ARQ, which is not especially different from what we were looking at earlier. We have some tooling ready for setting up the things we're going to need when we're running jobs. So you have a bit like in something like AIOHTTP, where you have startup coroutines for setting up, say, your database connection. You can do the same thing here. So you have startup and shutdown, where we can add to this context, which is the first argument to any job we set up, any function we set up. And I'm trying to remember here if I'll have an example of retrying jobs. So there's an exception that you can raise which will retry the job. And that is what is raised if you shut down the worker and the jobs haven't had time to finish. So any job that gets shut down, that gets stopped because the worker shuts down, will automatically be re-enqueued next time, because the job is not removed from the sorted set until it's been finished. So the problem with RQ is So I rewrote the Heroku worker, which basically deals with shutdown behavior in Heroku, because Heroku workers shut down variably. That was killing us generating invoices, for example, which is one of our slower jobs. And so when I built or rebuilt ARQ, I built this principle that your job might run twice, but it will always run at least once. And so it's your job to then take care of the fact it might happen more times, but if it shuts down, it'll get re-enqueued.
Okay, and in case your job runs multiple times, I guess you get only one result, or
it runs twice. That's your job then to use an idempotency key, or to use a transaction, or to do something in Redis to say, has this job already started? That's your problem, but there's a kind of principle that you can never have exactly once, and so it prefers multiple times over. I mean, take an example of sending your customer an email, their invoice each month. They would get a bit confused if they received it 3 times, but that's still better than them not receiving it at all. And that's normally the case.
Any question, anybody? And okay, so one last question, and then I ask the next speaker to please come up slowly and set up. There is no next speaker. Okay. So do you have any experience like releasing the GIL in like C extensions and stuff like that, and writing those, and if you can speak about how you can do it, if there are some tools that one can easily use.
So I haven't released in PyPy C extensions. Pydantic, we've just had a big effort as a community to, lots of other people did lots of work on it, which is really cool to see. The whole thing is now compiled with Python, which made it, I think, about 50% faster for lots of stuff. But there's some tweaks you have to make to the Python, but it's still valid as normal Python. So on environments like Windows, where we don't have those binaries available, it still just works exactly the same. So not directly, no.
Okay, that's cool. If there are no more questions, we can thank the speaker. Thank you very much, Samuel.